Hello, everyone, and thank you for joining us for today's presentations in in-vehicle sensing using near-infrared light for driver and occupant monitoring. I appreciate you taking the time to be here. Just a little background about Radiant. We are a light and color measurement company, and we've been designing and manufacturing scientific grade solutions for over 25 years to support our global customer base. Today, I'm happy to share our experience using light for sensing and look at how manufacturers utilize and ensure the performance of near infrared light sources for various applications. Okay, so for today's agenda, we'll cover the following. So we'll start off with in-cabin sensing. We'll look at the reasons, regulations, and methods for various sensing technologies. We'll then merge the focus over to near-infrared light, which is the basis around this presentation. We'll look at near-infrared light in regards to the technologies that are utilized, primarily laser and LEDs, and then we'll look at the benefits and applications that each one of those technologies are well suited for. We'll validate the performance considerations of those two technologies, and then we'll look to wrap up the presentation when looking at measuring these near-infrared light sources. So ensuring accurate distribution and output can be quantified, and of course, discussing how we go about that characterization process with a one-test solution to really look at all lighting geometries. So let's talk about the motivation behind in-vehicle sensing and look at the current systems and trends. Why are initiatives for sensing becoming so popular inside the vehicle? Take a look at this image as an example. We're not quite here yet. Some experts say we're still decades away from really being into fully autonomous cars. However, the industry is on its way. So while the technology is emerging, let's take a look at sort of what the reality is today. We're really more in a semi-autonomous vehicle situation. So like the SAE level 2 and level 3 designated vehicles featuring assistance systems and autopilot modes, much more of the vehicle is being taken over. So things like controlling the steering of the vehicle allows users, drivers to take their hands off the steering wheel. And as hands become free, however, our eyes soon start to drift from the road to various dangerous situations. And when cars aren't able to drive themselves without intervention, we could run into a significant situation. According to the National Highways Traffic Safety Administration, the process of sending or reading a text can take a driver's eyes off the road for a full 5 seconds. If you're traveling at around 55 miles per hour, that's the equivalent of driving the length of a football field while wearing a blindfold. So the interaction while we move into this autonomous world becomes really critical to be able to monitor what the driver's doing when the driver decides not to pay attention to the road. In-cabin sensing systems assist drivers in safe operations of vehicles at any level below full autonomy and ensure the safety of all passengers inside the vehicle. The technical category of systems we're discussing are automotive interior monitoring systems, known as IMS, which break down into two categories: driver monitor systems, which we'll say DMS through this presentation, and occupant monitor systems, which will be known as OMS. Driver monitor systems reduce the risks of accident and injury due to driver distraction and drowsiness. These systems are evolving for applications like facial recognition for vehicle personalization or mood sensing for cockpit adjustments. These systems have been available as premium technologies in luxury vehicles since I think as early as 2006 in a Lexus, and we're now seeing mandates from governing bodies in both the European Union and the United States to integrate DMS as a standard safety requirement. When we look at occupant monitoring systems, we're really still at the early stages of development and integration. Initial systems will adjust child presence detection and other forms of occupant detection and biometric monitoring to improve passenger safety. Both the Euro NCAP and the US OEMs have their eyes on integration dates for OMS as well, going into the near future, but likely to sort of be integrated well beyond 2025. Let's discuss the regulations that are already in progress. All of these initiatives we'll discuss emerged between 2018 and 2019 and give us basically a 3 to 5 year window for implementation. The first is a mandate for DMS in Europe. Based on general safety regulations from the EU Commission, driver monitor systems will become a mandatory integration process in safety awareness for European vehicles beginning 2022. They'll really break down into the following, which are called out in this new standard. So looking at driver drowsiness and attention warning, advanced driver distraction warnings, emergency braking systems, intelligent speed assistance, emergency lane keeping. These wrapped into a DMS platform will be absolutely critical for saving lives. And the EU has actually estimated that between the integration of this mandatory feature and 2037, they believe that more than 21,000 people's lives could be saved from fewer deaths on the road due to driver-related distractions. This is an astronomical number that really needs to be taken into consideration. When we look at things sort of happening on the OMS side in Europe, they're not as far along. So as I mentioned, really the roadmap pushes out beyond 2025. And the primary interest within the standard right now is around child presence detection, which would allow the vehicle to warn the driver or those inside the vehicle if a child has been left behind. We see this as a problem around the world all the time, where unfortunately children get left in their vehicles and end up in really unfortunate situations. So I really believe that this is a primary technology that vehicles need to integrate. Being able to detect a child, whether he's been left alone or not, is really critical to saving lives. And it's such an easy type of technology to implement as we move towards that DMS platform. In the United States, similar initiatives have begun to regulate monitoring systems. However, we're not quite as far along. The Stay Away for Everyone, also known as the SAFE Act of 2020, kicks off the investigation towards legislation of DMS. So again, here we're looking at driver distraction, driver disengagement, automation complacency, and misuse of ADAS. Really, the driver distraction, driver disengagement are going to lead the Safety Awareness Act, though, moving forward. Similarly, the US is looking at regulations to integrate OMS primarily for child detection. So looking at associations of the global automakers and the Alliance of Automobile Manufacturers voluntarily commit to standardized rear seat reminders by 2025. So this is a secondary group really looking to take this on. Of course, helping overcome trauma for children alone in rear seats, also known as Hot Cars Act, was started in 2019, is helping really push and lead that charge. Regarding the installations of OMS though, really we're looking for alerts in the rear seat while exiting or entering a vehicle, detect movement after the vehicle is parked and locked, and of course, monitoring the general biometrics of any passengers found in the rear seat. Driver awareness and occupant wellness have various indicators, from eye position to body posture to pulse and temperature. There's also the considerations for placement within the vehicle, the interface and the interference from various objects, lighting, or occupants in the cabin. For this reason, there are a number of sensing technologies that may be considered for DMS or OMS. The first one we generally see are camera technology. So cameras can help detect yawning, eye closing, actions like drinking, smoking, or being on the phone, of course. Radar can provide vital sign detection, such as respiration, heart rate, as well as detect and classify occupants like kids or pets. Thermal cameras can also detect occupants and determine aspects like heat levels within the vehicle, becoming unsafe for children or pets who might be left unattended. And finally, EKG can provide heart rate variability data used for drowsiness detection. We see this technology primarily implemented in steering wheels at this moment, where the other three technologies really have a diverse implementation throughout the entire interior of the car. One of the primary methods of sensing relies on near-infrared or NIR light, which is the focus of our presentation. NIR wavelengths are above the visible spectrum, ranging from around 780 to around 1400 nanometers, sometimes extending even out to 2500 nanometers. Since these wavelengths are invisible to the human eye, they are not distracting when they're cast into your visual field, which is really critical and important when driving at night. They're also not impacted by visible light and therefore can operate effectively in any ambient light condition, allowing them to see the human eye or various aspects of the car and create an efficient distribution for a camera to perceive them in night or daytime settings. NIR light-based systems can also detect your eyes through glasses and sunglasses, which causes problems for visible light systems and eye tracking applications. Like any sensing system, NIR systems function by receiving a signal from the environment. NIR light is cast into the cabin of the vehicle or onto the driver's face. This light illuminates an area for an IR-sensitive camera to physically see the environment. When pulsed or cast in a dot pattern, NIR light can be used to determine object depth, curvature, shape, and size. Just to give you an idea of how prevalent NIR systems are, here are some of the trends we've observed for DMS and OMS integrations. Some of these features are included as part of OMS overall driver assistance systems, integrated sensors both inside and outside of the vehicle, concept like those found within the Audi and BMW models that were showcased back at CES 2020, and of course, vehicles like the new 2021 Mercedes-Benz S-Class that tracks drivers' gaze for unique applications that enable the instrument cluster to actually be displayed in 3D, which is a great use of this technology for non-safety related features. In most cases, we see NIR light sources and cameras that are used to provide information related to the driver, including eye and gaze tracking, as well as head rotation and position. Many DMS not included here monitor driver fatigue by other methods such as steering wheel rotation, lane departure, irregular pedal use. Such systems are used by OEMs like Honda, the driver attention monitor platform, Jaguar's Land Rover, the driver condition monitor, Mercedes-Benz, attention assist, Volvo's alert control, Volkswagen's fatigue detection, and many others include these technologies, as you can see here in the presentation. In the case of OMS, most markets seem to rely on radar and ultrasonic sensors. However, NIR systems are being developed by tier suppliers for OMS applications. Many OEMs like General Motors or Nissan have integrated OMS into their vehicles, which rely on rear door opening and closing as indicators rather than physical sensor systems. When we look at the applications for NIR-based sensing, we see a primary application will be safety systems like DMS, by the way of eye tracking and head position, as well as some emerging OMS systems. Secondarily, we expect to see systems that focus on experience, like facial ID for personalization or gesture recognition. Eye gaze and tracking, of course, the primary application for this NIR light is for sensing and tracking the driver's eyes movement or gaze, as well as pupil dilation, blink rate, duration, and whether the eyes are open or closed. Pupil dilation, blink rate, eyelid movement can indicate fatigue. Changes in gaze can indicate whether a driver is focused on the road or distracted by other elements like their smartphone, controls inside the vehicle, or generally other passengers. Presence and position focuses on head position and movement, which can also indicate a driver's focus, alertness, or fatigue. NIR systems can track points of the driver's face, like the eyes, nose, mouth, to understand their head position, their indication, and their general awareness. General presence detection is also important, not only to identify a driver to begin positioning points for the head and eye tracking, but to potentially initiate other functions inside the vehicle when the driver is detected, like prompting a seatbelt check, alerts, or personalization features. Occupant detection is where we look at NIR systems that could be used in the OMS application to detect other occupants inside the vehicle, initializing monitoring functions for rear seat passengers like children. These systems could also make real-time adjustments to the vehicle's cabin, from disabling airbags for smaller passengers to preconditioning the vehicle's interior in the event of an accident, responding to each occupant's situational awareness and positioning. Facial recognition is where we're looking at it's what we're basically all used to because we have smartphones. So we're accustomed to the idea of facial recognition in devices that we use today in our everyday lives. So we're looking at taking that facial ID that we would see in a cell phone and bring it into an automotive facial recognition platform. Again, using similar technology that we do see in the consumer electronics industry. The principal aspect of facial recognition has been used for identification to determine unique users. In DMS, facial recognition could enable personalization, like seat and mirror settings. It could also be used to identify facial expressions for ambient adjustments like lighting, temperature, or even music. An important note of facial recognition is that recognition implies the identification of a particular user. Some descriptions of current DMS technology imply facial recognition when they only mean that the DMS can track facial features. This is the difference between identifying a face and, of course, identifying John's face. And then finally, we look at gesture recognition. NIR Lite is used for gesture recognition in several consumer electronic applications. A classic example would be like the old Microsoft Xbox Kinect as an example. As vehicles become more hands-free, gesture recognition could enable any number of controls currently provided by analog buttons to really be heightened or exposed to unrelated touchscreen perspectives. So let's take a look at light sources that produce illumination and signals for NIR sensing systems, how they differ, and their general applications. NIR sensing systems rely on either NIR LEDs or laser sources to produce invisible light that is reflected off an object in a cabin. Both types of sources can be used in the same application, including object detection, identification, and of course, tracking. NIR lights, sometimes called IR LEDs or infrared emitting diodes, are used in devices from facial recognition systems to security cameras all around the world. They cast a wide distribution of light at a very short range. Generally, they provide light for 2D IR cameras using a majority of DMS that we've seen so far in the technology world today. NIR lasers are precise and very efficient. They're useful in long-range sensing, are easily directed and diffracted to produce structured light patterns like arrays of dots that are common in normal facial recognition patterns like our cell phones. As we talk about laser sources in this presentation, we'll refer to them specifically as VCSELs, or vertical cavity surface emitting lasers. As with the consumer devices that feature facial ID, VCSELs are one of the most commonly integrated sensing technologies for these applications we see, and they offer a huge benefit to the DMS and OMS applications in the cockpit or cabin of the automotive vehicle. This is an eye chart that is not exhaustive of the differences between LEDs and lasers. We'll unload some of these points in the following slides. The basic takeaway is that there are only a handful of differentiators between these sources, and no single source is really best for all application. In some cases, it really comes down to manufacturer presence or preference. In general, LEDs distribute light over a wider area. However, their distributions are shorter range than lasers. Their wavelengths are also less stable over temperature. That is, their wavelengths can actually shift depending on temperature of their environment, which is something we need to consider. Also, their light is incoherent. That is, their photons do not travel in sync with one another, making it difficult to direct LED light without spatial objects or spatial optics. However, they are generally eye safe and are lower cost than lasers for implementation. VCSELs are up and coming for in-vehicle sensing applications chosen for their advantages in precision, range, optical efficiency, temperature stability, and general beam quality, which means that they can produce various precise beams of light that maintain their general quality and efficiency over different distances. However, they have the additional safety requirements and are usually higher cost for implementation. Another point, all lasers, VCSELs specifically, are very coherent, which goes back to their precision aspect that we need to take into consideration as their photons do travel in sync across their distribution. So let's break down these two technologies a little further. This image illustrates the differences in geometry of each type of light source. As we mentioned, LEDs are advantageous for NIR sensing because they cast a wide distribution of NIR light. With a much larger spot size than laser sources, we can illuminate a larger area with LEDs pretty easily and effectively, giving IR cameras the light they need to see inside the vehicle at all daytimes. VCSEL lasers produce a very precise, uniform spatial illumination pattern in a small circular spot, much, much smaller than your LED source. The distribution of light of the light source is output in 3 dimensions in angular space. The beam angle is what determines how much area we can effectively cover for sensing. This is just an example of how the beam angle of a source determines the overall scope of the sensing area. Say we have a DMS with an NIR LED integrated into the steering wheel column or maybe even the instrument panel at about 0.5 meters away from the driver's face. If our LED has a beam angle of, let's say, plus or minus 20 degrees, that means when the light reaches our driver, we're covering about 0.36 meters or 1.25 feet of area. Hopefully, this covers the potential driver's height and position to keep our sensing systems working. If not, we may look at various sources or at adding additional emitting areas. NIR LEDs can have a very wide beam angle. A standard LED beam angle is about 120 degrees or plus or minus 60 degrees, as you might see it on spec sheets. For sensing applications at close ranges like inside the vehicle, LED beam angles are typically narrowed using optical elements to maximize the power across the required sensing area. NIR lasers produce a very focused point of light. Out of the box, these sources really are not going to provide adequate distribution of light to cover the face of our driver. To create the wide beam angle necessary to cover the driver's face, diffractive optical elements, also known as DOEs, can be used to diffract a single laser beam into multiple points of light. A DOE has tiny apertures that split the laser into multiple emission points when the light is cast through it. These points create structured light patterns that can have a broad distribution, just like LEDs, but with a longer range. And as their intensity remains more consistent over distance, this could be useful in OMS where a larger 3D space of the interior cabin is actually being scanned. Because of the differences in coherence, LEDs will lose power and dissipate much sooner than a beam of laser light, resulting in a shorter range sensing capability. Lasers maintain power across longer distances with more uniform beam quality on the points that are farther away. The range limit of either source depends on the initial power of the light source. You can get a more powerful source and sense objects farther away. A more powerful source may have safety implications though. However, we can generally say that light sources used for close proximity sensing in the vehicle are on the low end in terms of power requirements. In terms of range, both LEDs and lasers could likely do the job in most cases. Here's some potential integration areas of NIR sensing systems. LEDs are effective in integration areas with close proximity to the driver or the occupant. A longer range application like OMS adopt NIR-based sensing systems like lasers that may come into play, especially where integration areas call for more precisely directed light to target specific areas of the cabin. The geometric characteristics we've observed for these light sources typically will determine their application in the vehicle. So let's talk about some of the applications for NIR and then basically breaking down LEDs and lasers, both in their current systems and the potential applications that we see them for the future. Here, we're looking for light source to illuminate the cabin for 2D imaging by an IR sensing camera. Because they cast a wide distribution of light, NIR LEDs provide the illumination necessary for IR cameras to physically see the scene inside the vehicle. These cameras capture 2D images of a scene much like a visible camera would, only, as we recall from earlier in the presentation, using NIR light doesn't actually detract the driver and can be used in a range of lighting conditions. 2D illumination is the application we see in a vast majority of DMS and States vehicles. Here, an NIR LED and camera are integrated into the center stack, dashboard, or maybe even the steering wheel. The LED is typically pulsed to produce higher intensity light in very short bursts, in this case, into the face of the driver. The light is reflected back to the IR camera and the light is converted to an electronic signal that produces an IR image. Here's an example of such a system where EyeSight Technologies is using NIR LEDs to provide illumination for an IR camera. Advanced facial processing software tracks the driver's gaze direction, pupil dilation, eye openness, and even head position. 2D images are great, but 3D information is also really handy. For instance, it's difficult for a computer to tell from a 2D image the depth of a physical object, maybe the rotation of a head or the precise contours of a face. In situations where we want to go beyond 2D images, reflection time, angle, light intensity can also give us additional information for what we're looking for. To capture 3D information in terms of an object surface, a time of flight or TOF function is used. At a basic level, a single LED or laser source could provide time of flight data that enables the system to detect and calculate the position and depth of the object. This could be used for OMS in detecting the number of positions or occupants in the car, or in a DMS fashion, go beyond the presence detection. This could provide information like focus depth of the facial recognition scan. In these cases, the LEDs emit a pulse of light, which is reflected from an object surface back to the IR camera or sensor. Depending on how long that light takes to return to the sensor, its time of flight, the system can calculate where or how far the object surface may be. A method called stereo vision works by triangulating the reflections of NIR light, casting a light from a source onto an object surface, and then receiving the light reflecting using multiple sensors. Stereo vision can enable software to determine basic object depth and position in a limited 3D space. The more sensors we use to detect the light reflection, the more dimensional information we get. Other 3D sensing relies on structuring light into a known pattern and interpreting that 3D information based on deviations in the pattern's reflections. A laser emitted through a DOE casts an array of tiny invisible dots onto a person's face, as an example. When the light from each of the dots is reflected back from the object and received again by the NIR sensor, the device uses deformations of dots from their original position and shapes to determine the contours of the object. Effectively, the NIR structured light grid creates a general map of the object's 3D features. Structured light sensing is a common method used in biometric security like facial ID, for instance, for unlocking our smartphones or potentially initiating secure vehicle functions. It can also be used for object sensing and identification throughout the vehicle, enabling precise depth and shape of sensing in the OMS application. Here's just a visual example of what structured light patterns look like. The number of points in a pattern vary on the system, but can include tens of thousands of tiny dots. The patterns vary by application, and the points could be dots or short lines, whichever pattern the system is expecting to receive. The effectiveness of each of these applications depends on the performance of each of the sensing systems and components. In particular, let's look at the performance considerations for NIR light sources. What are the qualities we need to look at to evaluate these sources and their general performance to ensure that they are the right fit for the applications that we're considering? So when we look at performance indicators, we want to understand things like, does the light source provide enough intensity for the sensors to work correctly? Does the source provide too much light for the human eye to receive safely? And then, of course, is the scope or the pattern of the distribution generally accurate? First, let's talk about the impact of insufficient power or intensity. IR imaging is dependent on the amount of photons received by the IR sensor to decipher the elements in the environment. We need enough signal from the light bouncing off the objects in the cabin for the camera to distinguish objects from the background. The more powerful the light, the stronger the signal, reducing the impact of image noise that may be misinterpreted within the image. What we're referring to is the concept of signal to noise ratio, also known as SNR. NIR light sources must have sufficient enough intensity to optimize the signal to noise ratio for the receiving camera. Here we see the effect as we reduce the amount of light the camera receives to produce an image. Soon, the target object becomes nearly indistinguishable from the background noise. If we plot this signal of the bright object on the left, it is high enough above the noise threshold that is clearly distinguishable. If we plot the signal of the dim object on the right, the signal is mostly below the noise threshold, making it really hard to pick out. Our NIR light source should produce light with enough intensity to enable a proper signal to noise ratio for imaging. NIR light is outside the visible spectrum. We can't see it, and so our eyes don't respond to it. Our pupils don't contract, we don't blink. NIR light does not trigger any level of inversion response from us. Sensing devices emit light at humans and sometimes even directly into our face or eyes, so there's a need to measure the NIR source for maximum eye-safe emission intensity. For this reason, NIR light sources are regulated for maximum output power to ensure general safety awareness. LEDs are generally considered to be intrinsically safe. They're governed by the same safety standards as lasers, but their power can be higher while remaining within a safe classification. Lasers are regulated by IEC, or EN 60825-1, which sets the maximum permissible exposure limits for different classes of sources. Manufacturers may further restrict their tolerances to specify classes of light sources for internal requirements. A laser's class is dependent on its wavelength, exposure time, timing of source, and its emission geometry. Ensuring lasers and LEDs meet minimum tolerances and do not exceed maximum tolerances for output requires the evaluation of these sources on a total output of distribution and power at each point across the entire distribution field. We've discussed light sources that emit in 3D angular space. The performance of the source is determined by its emissions in this space. There are a couple notable measurements and values that we need to describe and look at when considering these emissions. We start with light output in several directions. Here's a directional emission of light in angular space. The space is limited by our source's beam angle. The power radiated uniformly by the source in all directions is called radiant flux. This value is measured in watts. We can think of this as a total NIR light that the source produces in 3D space. If we look at the 3D volumetric slice of this space, we get a solid angle of light source, which is measured in steradians. Radiant intensity is the power of light at a given angle, measured in watts per steradian. Radiant intensity is literally the radiant flux of the total light emitted in space divided by the solid angle or section of the 3D distribution. While radiant flux can give us the source's total output power, radiant intensity can give us the power at a specific directional point in angular space. The performance of a source also has to do with the integrity of the distribution. We may want to measure radiant intensity at one point in the distribution, or generally another. Performance can also be determined by the uniformity of a source. How does the radiant intensity change from place to place? Are there hot spots? What's the fall off of the intensity to the edge of the distribution area? For wider distributions, we're often looking for uniformity across a central zone where the intensity is generally at its highest. And finally, we want to look at the source's beam distribution and verify that it is the right shape, not just a circular distribution, but an angular space as well. Is the intensity correct in terms of azimuth or inclination? Is it achieving the right peaks that we're looking for in its distribution? If we're really looking to evaluate a structured light pattern, we maybe want to understand if all the dots are present. Are any of the dots in the wrong place? Is each sub-pattern of the pattern correct? For instance, are these lines of the dots the same distance apart in each section? There's a lot to really take into consideration as we look at the distribution of IR light. This really brings us to the measurement methods that help us quantify these various performance characteristics of NIR light sources and all types of geometries that are associated with them. Geometry of a light source distribution is very relevant because it affects the way we approach the measurement. Are we looking at a broader angle distribution like that of an LED? Or do we want to characterize thousands of dots in a structured light pattern like that produced by a laser? Ideally, our measurement system can address both of these scenarios, generally to save time, complexity, and cost in our light source evaluation process. Because light is emitted in angular space, determining if NIR light sources produce sufficient and safe intensity for an application requires radiometric measurements of the complete angular distribution of the light source. Each angle needs to be measured. Sometimes these angular emissions are actually quite broad, as is the case with LEDs and dot patterns, as I've mentioned already. The challenge for measurement is to capture all of these angular emissions as completely and quickly as generally possible. Goniometers have been used for light source characterization and modeling for a really long time because they're able to capture the complete output of a light source in three-dimensional space. They do this by rotating the photodetector and the source relative to one another, measuring the light distribution generally at every angle. But there are limitations, of course. First, you need a really large space to rotate the photodetector around the light source. This means big pieces of equipment and often huge costs and complexities that are associated with bringing that together. Measurement time is also generally an issue. Because of how many positions need to be measured, a complete 3D light source measurement can take hours. A goniometer is really only practical when you can afford this time, space, and complexity. Often, we see goniometers being used in the lab environment where precision may outweigh the various challenges that I just mentioned. But it's absolutely not going to help you quantify or qualify the control of a production flow process. Finally, a system like this is very impractical for measuring structured light dot patterns. You don't really need a complete 360-degree rotation to measure a dot pattern. And at the end of the day, what you really want is a system that can correctly evaluate the pattern positions of the dots as well as its intensity. Which brings us to the challenge of measuring patterns. Patterns produced by NIR sources are particularly challenging to measure, not only because the need to measure intensity over angle, but also the dimensional aspects we need to consider. Are the expected number of dots being emitted? Are the dots forming the correct pattern? What is the intensity of each dot? And where are the highest and lowest intensity dots? Ensuring accuracy for these patterns could mean measuring, counting, and locating tens of thousands of points, which is common for applications like facial recognition. Traditional methods for pattern measurements utilize a wall or a screen. The pattern is cast onto the surface and a photodetector takes a measurement of what is reflected. The limitations of this method have everything to do with the fact that you're not really measuring the light source. Instead of direct radiant intensity of the measurement, the light from the source, you're now measuring the irradiance, which is the light on the wall. Additionally, this method is limited in its understanding of the angular aspect of the light distribution. This is where a goniometer would normally excel at characterizing the light source in angular space, but when cast on a wall, the light loses some of its dimensionality. This traditional method also demands a larger physical space. You need a big screen or a wall and enough distance to position the camera to capture the overall distribution. Not to mention, the resolution you get from this kind of measurement could be reduced depending on your distance to the source or the general resolution of the camera technology you might be using. So, what kind of measurement solution do we really need? We need something that combines the benefits of the angular measurement from the goniometer with the dimensional pattern measurements from the on-the-wall approach. Since neither of these are giving us all of the data that we actually require, our NIR measurement system must include the following: the ability to capture all angular emissions of light, measure accurate radiant values, verify the intensity and position of thousands of dots, and do this with speed and minimal equipment. This is where specialized optics truly help. FOURIER optics provide image-based measurement systems with maximum data for NIR source qualification in angular space. Unlike traditional measurement methods, a FOURIER optics lens solution is compact, fully integrated into a single camera system. It enables direct measurements of NIR LEDs or lasers in angular space. The solution here from Radian is a lens integrated with an image-based radiometric metrology system. Using calibrations, the solution measures NIR sources with wavelengths like 850 or 940 nanometers. Applying FOURIER optics to image-based measurements, this solution measures angular emissions out to plus or minus 70 degrees in a single image without rotating the system or source at all. FOURIER optics capture directional distribution of light rays emanating from a single point, which creates a cone like we see on the image here on the left, and transforms them to a lateral distribution, all light rays parallel, as seen on the image on the right. This enables the connected image system to capture the entire visible cone of the angular light rays on a single focal plane, which would be its internal image sensor. FOURIER optics allow the measurement system to capture all angular light emissions at once, as well as visualize and measure angular emissions simultaneously in a single image. This is extremely fast as compared with traditional methods. Once the system is in position, measurement of the entire angular distribution can be completed in less than 1 second. That means total angular intensity measured for a source is done in a blink of an eye. FOURIER optics also eliminate the need to rotate the image system or the light source to capture angular light emissions. Both elements stay in one place and the image is captured, and multiple analyses can be performed on the angular distribution of light after that. At Radiant, we've developed a system that can measure plus or minus 70 degrees or 140 degrees, as it might be known, across the emitting area. Our system is integrated with a high-resolution radiometric sensor that achieves 0.05 degrees of angular resolution per sensor pixel. That means we measure points and discern details that are less than 0.05 degrees apart in angular space. Thanks to FOURIER optics and imaging, what used to take up a lot of space for a lab measurement, you can now set up on your benchtop or mount above a production line. Instead of a goniometer or wall-based measurement approach, we have a single camera lens solution that is extremely compact with very little setup or configuration to get running. The price point of a turnkey system versus a large or multi-component system is also significantly reduced. Of course, a measurement system isn't complete without the accompanying software. Using a software package developed for NIR light source analysis provides a test suite that is specific to radiometric measurements and a unique geometry of identifying patterns of NIR LEDs and lasers. An NIR measurement software package will work with an imaging-based metrology system to help us understand and characterize and analyze various images for the following quantities. We'll look at total flux, max power, radiant intensity, points of interest, POI, power, pixel solid angle, inclination solid angle, uniformity, hotspots, fall off angle, inclination azimuth, and structured light pattern statistics. Being able to do this in a single turnkey software platform is a huge advantage. Here's a measurement image of an infrared LED using Radiance Fourier optics lens system. This shows a polar plot and cross-section of the angular distribution, where the radiant intensity is measured as a function of angle of the light being distributed. You can see that the distribution extends from plus or minus 70 degrees for the field of view. In the measurement image, false color is used to represent the radiant intensity, where the red color is more intense, with intensity decreasing outwards towards the purple colored area. Again, measurement of a complete angular distribution takes less than 1 second for acquisition and analysis. We can also define a region for measurement. In this case, we're looking for a full width half maximum region. Determining the full width half maximum of the light source is kind of what it sounds like. We're measuring an area that is full width of the source distribution where we're receiving at least half of the maximum radiant intensity. The output value that we get from this area is usable light over the source that is produced in angular space. We probably won't achieve the minimum intensity limits for our application beyond this area. So it's most useful to use full width half max when measuring a source's intensity. An NIR software package containing dot source analysis functions can define points and output values for thousands of dots in a structured light pattern. In this example, Radiance NIR measurement software on the left, we have a series of analyses that can run in a sequence depending on which are checked. Multiple analyses can be run, each applying various unique pass-fail tolerances if necessary for rapid automated quality control. From a measurement image perspective, the software automatically identifies all the points in the pattern and gives each one of them their own unique intensity value. We can also report each dot's position in both pixel location on the image sensor as well as the angular location in 3D space. A dot source analysis function can count all the dots, create a pass-fail on the missing points or inaccurate dots, and give a comprehensive information about each dot found within the scene. This is a close-up of a dot source analysis image in the Radiance NIR measurement software. Here we can see the kind of data we get just by hovering over the dot in the measurement image. This particular dot has an intensity of 254.1 milliwatts per steradian and is located at an inclination of 11.28 degrees and azimuth of 20.94 degrees. There are a number of data points we can output for structured light patterns. These can be exported to spreadsheets or used in pass-fail quality control processes. So again, locations of pixels in general XY space, the location for the inclination and azimuth angles, the intensity in watts per steradian, peak average intensity, peak solid angle, pixels at a maximum peak, spot power uniformity, maximum peak radiance, total flux, diffuse optical element flux, and of course, we can finally export the variable images that are required. Combining a Fourier optics lens and imaging system, we have a measurement solution that significantly reduces the cost and general complexity of an NIR light source for testing and enables the integration into production level for quality operations. NIR measurement software ensures that our measurement approach is both comprehensive and specific to the source, the geometry, and the measurement parameters. The same solution can be used to evaluate light sources of any distribution and geometry, capturing an array of radiometric data and geometric performance indicators. Plus, you also have the same tools that can be utilized at the lab level, at quality assurance, or for complete inline, which allows you to record millions of data points and enable truly 100% control and design in the manufacturing process. So let's wrap up the presentation. We've discussed the needs of the regulations for driving integration of in-cabin sensing systems, in particular focused on the EU and the US regulations for new vehicles. DMS and OMS are two systems that rely on sensing methods to ensure the safety of drivers and passengers in the vehicle. It's evident from the current systems on the market that NIR light-based sensing systems continue to be popular, especially for driver position and eye tracking. The performance of NIR sensing systems relies on the part of the performance of the NIR light sources such as LEDs and lasers, which must be evaluated for their angular intensity and the quality of their general distribution. An NIR measurement solution that uses Fourier optics imaging and NIR measurement software is faster and more efficient than traditional methods and can be used to evaluate NIR light sources at all aspects of the product lifecycle. Thank you for your attention. If you have any questions or would like further information, please feel free to reach out to us at info@radiantvs.com. And please feel free to take a look at our website at radiantvisionsystems.com. Appreciate everyone's time and look forward to chatting with you in the future.